Well guys, we're up to lesson 6 today of the forces unit, and we're going to be looking at distance time graphs. So today's objectives, you're going to be able to describe the difference between distance and displacement, kind of follow on from last week. Describe the difference between speed and velocity, again from last week. But today you're going to be able to draw and interpret distance time graphs. And then you'll be able to calculate the speed velocity from one of these graphs. And at a higher level, you'll be able to draw tangents to curved lines to work out speed when an object is accelerating or indeed decelerating. Okay, before we begin then, today's video from the Fuse School again, an excellent video, only about 3 minutes long, displacement time graphs. If you could just pause this video and watch that one, come back to this to do the notes. Okay, haven't watched that video. Let's just check the spec, check to see what you need to know. You need to know that velocity of an object is its speed in a given direction. It's a vector quantity. You should be able to explain the vector scalar distinction. I've been drumming that in the assessments you've been doing. And for higher tier, you should be able to explain qualitatively with examples that motion in a circle involves constant speed but changing velocity. We will come back to that one and not really look at that today. The distance-time relationship, if an object moves around a straight line, the distance traveled can be represented by a distance-time graph or displacement-time graph. The speed of an object can be calculated from the gradient. For the higher tier, we'll talk about acceleration by drawing a tangent. And you should be able to draw your own distance-time graphs and also interpret them. And that will be today's assessment. So you'll be able to determine speed from a distance-time graph. Okay, here's the example I want to use for you to look at. You saw some in the Fuse video, but here's an example. If I just draw some lines on here, we're going to have a look at each section of the graph. So the first section goes from 0 displacement, from the start, if you like, up to 10 in a time of 20 seconds. Because it's a straight line, that means it's traveling at a steady speed. The second part of this graph is a horizontal line. Now, a horizontal line means it stays at 10 meters. So this object is stationary at that point. From 40 to 60, you can see it again moves, again with a straight line, but this time the line is steeper, and the steeper line represents a faster, but because it's straight, a steady speed. And then the line coming back down means it's turned around. It comes in the opposite direction. And it's a steady speed again, because it's a straight line, and it's in the opposite direction. If we were referring to velocity here, it would be a minus velocity. The number would be minus because velocity is a scalar quantity. So I'd like you to transfer this into your books now. If I pause the video and do a sketch of this in your book. It doesn't have to be too accurate, but with the annotations. Okay, just some questions, and you can add the answers to your diagram that you've just drawn in your book. What is the speed during the first 20 seconds? So hopefully you're thinking about that. Speed is distance over time. It travels 10 meters in 20 seconds. So it's 10 divided by 20 is a half, or 0.5 meters per second. How far is the object from the start after 60 seconds? So you can see after 60 seconds, it has traveled 40 meters. What is the speed during the last 40 seconds? Well, from 60 to 100 is the last 40 seconds, and at 60 it was 40 meters away, so it's traveled 40 meters in 40 seconds, so the speed would be 1 meters per second. And if you were asked for velocity there, it would be minus 1 meter per second because it's in the opposite direction. We should ascertain which is the positive and negative direction. When was the object traveling the fastest? You're looking for the steepest part of the graph. The steepest part would be from 40 to 60, so it would be between 40 and 60 seconds. If you want to add some annotations to your example in your book. You're now going to write some notes just to explain it. Not much, it'll take you a few minutes to get down these notes, but from these graphs you must remember a horizontal line means 0 speed or velocity, so the object is stationary. A straight diagonal line means a steady speed or velocity. A steeper line means faster speed or velocity. A gradient of the line is its object's speed or velocity. And a line going downwards means it's got a minus velocity or speed in the opposite direction. And finally, in the real world, you don't get straight lines. Things will speed up and slow down. So curved line means changing speed, acceleration. So the next slide describes that. But if you want to pause this video and get those notes down. Okay, here's another example. Just make sure you got it. You don't need to write this one down, I don't feel. What was the velocity in the first 20 seconds? Well, it travels 30 meters in 20 seconds, so that's 1.5. We're assuming going that direction is a positive. What was the velocity between 20 and 40? Between 20 and 40, it travels 10 meters in 20 seconds, so that's 0.5. When was a person traveling the fastest? Well, that would be on his return journey from 40 to 100 because he travels 40 meters in 20 seconds, so it would be 2 meters per second. It would be minus 2 meters per second in terms of velocity. And what was the average speed for the first 40 seconds? An average would be the distance over time. Total distance is 40, total times 40 is 1 meter per second. Okay, as I said, in reality, graphs are more curves than straight line. So this is a typical kind of graph of somebody who might run 40 meters, the kind of curve that you would get. In the first section, we started from rest, then you would accelerate. So the graph would curve upwards, and that would represent acceleration. In the middle section, where it straightens out a bit, you would be going a steady speed, you know that already. And in the last section there, where it curves towards the horizontal again, he's slowing down to come to a stop maybe at 40 meters. Okay, this is higher level stuff now, how you'd work out the speed from this. I'm going to show you how to do it, and you can draw this in your book as another example. So at this point here is accelerating. Let's just say we want to work out his speed at a certain point where the arrow's pointing. You would draw a tangent to the line. A tangent looks like that. A tangent shows the gradient of the line at that point. And to work out the tangent, the gradient, you'd use the distance traveled, which would be 0 to 60 meters here. In the time it takes, and for this tangent, we're just taking it across there to go from 15 seconds to 60. So a time of 45 seconds, and you'd work out the speed by using the equation, which is a tangent to the line. In this case, it would be 0.36 meters per second. Okay, so let's just check your lesson objectives again. You should know now what the difference between distance and displacement is, and speed and velocity, one of each being a scale and vector. You can interpret any distance time graphs, I hope now, and calculate the speed from any one. And then you can also learn how to draw the tangents, this higher level work. To test your skills today, to test your knowledge today, I've attached to show my homework this worksheet. It's up to you whether you can print it out and stick it in your book or you want to just write it out. I've made the graph, the table, very easy because I'm aware that you may well not have graph paper at home. You will not need it. You can just draw it out, a sensible scale in your book, possibly 1 centimeter for every second, and 1 centimeter or 2 centimeters for every meter, and you should be able to draw that graph. You must do this. The 10 questions are then going to be, your answers to 10 questions are going to be put into the Microsoft Forms, the assessment this week. So you must do this before you attempt the forms. If anybody attempts the forms without doing this, they will just be guessing, and I'll spot that. And you know that I'll follow you up. So I'm hoping if you do this, you'll find it very easy. And I'm again hoping that the scores, the average scores will be near 10, that most people in year 10 are getting this. So do this first, then go into the forms, and the forms looks like this, and you will enter your answers and hopefully get 10 marks. Thank you for listening. This is the end of lesson 6. In the next lesson, we'll be looking at velocity time graphs. Have a good week.